All right, I think most people are there now, but I'll just walk through these steps in case you're not sure how one of these questions works, right? What have I done? Well, they've given me this and they've said, look, differentiate it, see what happens, right? So here is what I get to once I've differentiated, which is convenient, isn't it? So I wonder if that was something close to what you guessed. You're like, oh yes, that's exactly what I was thinking. I wouldn't have been able to guess it, which is why we don't expect you to memorize this result, okay? But having been given it, you know how to differentiate. It's just, that's just chain rule. This is chain rule plus a product rule, right? Because that's U and that's V. And it all comes out in the wash, which is nice. So what do I do from line 3 to line 4? I'm integrating both sides with respect to x. That's what gets rid of the derivative, and it adds the constant in on this side. But of course, if I'm actually working out a definite integral, I don't need to worry about the constant when I'm evaluating. Okay? But just to make sure it actually works, okay, what happens? What's going to happen in here? So I'll evaluate it at the upper bound, and then subtract it from valuing it at the lower bound, right? So what am I going to get here? This is my first one. So square root of 1 minus 1 is just 0, okay? Plus 1 times sine inverse of 1. We'll come back to him in a second, okay? Minus, all right, we'll do it at the lower bound now. So I'm doing it at 0. So this is the square root of 1 minus 0, which is 1. And then plus 0 lots of, well, actually I don't care what the rest of it is because it's 0. Right? Okay, so what's sine inverse of 1? That's pi on 2. Okay, good. So that's a relief, right? We did actually come back to this. So our geometric argument landed us on the same conclusion as if you actually knew what the primitive function was. So that's a relief. Okay. Now let's do the next one because it's a little bit, you just got to be a little bit more careful, right? I get rid of this. Okay, so where did I go? I'm going from 0 to half. Okay, now being that this is not a graphing question, right? By the time you sort of get to the HSC, you'll be so deaf at these questions, you probably don't need to actually draw out anything. But I'm still going to draw out on the side here a nice rough diagram so I can work out and not get confused what my boundaries are. That's the most important part, okay? So what does this look like? Here is sine inverse, and there's 1. Okay, so up to half is here. Yes, so there's the actual area that I'm after. So the important thing is, okay, now when I turn this into a regular sine graph, right, like so, where is this area? It's here, right? Nestled up against the y-axis. Okay, so what x values, what new upper and lower boundaries am I going to have? It won't be 0 to half. What's it going to be? What angle corresponds to that? It's pi on 6, right? Which actually makes sense. Like even if you look at it, you know that that's pi on 2, right? So pi on 6, it's sort of to scale. If you've drawn it reasonably, you can guess that that's what you're going for. Okay. So now I can immediately write the equivalent sort of like this line here, right? I want my rectangle, which is around it, and then I want the new integral, new definite integral that I'm forming. Okay. So what's the area of the rectangle in this case? Yeah, it's just pi on 12, right? I'm going to go ahead and write the whole, like the actual length and breadth, just so I don't confuse myself later on and I can track down an error if that's like the source of my error. Then subtract, and now this new integral I'm forming, like you told me, it's from 0 to pi on 6, and I'm integrating sine. Okay? Now from there, it works just the same. So this, like we said, I think is pi on 12. This is going to be minus cos x, which is double negative, from 0 to pi on 6. Is that right? Yes? Because that'll be minus cos, wouldn't it? Minus up front. So pi on 12. Okay, what do we got here? What is cos pi on 6? That's root 3 on 2, right? And then cos of 0 is just 1. So this is minus 1. So that's it actually. There's not much else to do because they're just kind of all messy. You got an integer and a surd and a transcendental number which don't mix any of them. So that's it. You're done. You don't need to simplify that any further. Okay. Okay. Now, you're starting to get the hang of it, right? But some of the areas are trickier than others. So the next one that I've got, number 3, I'll show you a couple of tricks to do this one because there's two different ways to do it which are equally valid, but there's probably one which is better than the other. Okay. So what I'm asking you to do is, I think it's a negative one. So. Okay. So what does cos inverse look like? That's the one which is all above the axis, right? So it's looking like this. Okay, so there's -1. Minus root 3 on 2 is like 0.86 or 0.87 or something like that. So it's pretty close here, right? Minus root 3 on 2. And I'm going to go all the way up to the y-axis. So this is the area that I'm after. Okay, now this is actually worth drawing out, right? When I convert this from a cos inverse kind of diagram to a regular cos kind of diagram, where is the area? So this is the corresponding domain of cos, okay? Where's the area I'm after? Where's minus root 3 on 2? It's way down here, right? Okay, and there's 0. So the actual area I'm interested in is here. That's not very straight, but you get the idea. Okay? For regular cos. Okay? So the area I need to subtract, right, is this area here, right? I can get that rectangle, and then I subtract the green area. Okay? So you have to be careful though, because the green area is negative. Yes? So take note of that. What are the new bounds going to be? Sorry, actually, let's take a step back. What's the area of the rectangle first? That's the big thing. Then we'll cut out the green area. What is the area of the rectangle? What's the height? The height is just root 3 on 2. Okay. Now, what's the width of that rectangle? It's all the way from here up to whatever that value is. What is that value?
1.
How many guesses do we have left?
Now, one of the handy things about this, right, is that, you know, maybe you're trying to work out on this diagram what it's equal to, but you can actually come back to this diagram because we've restricted the domain of cos to land on cos inverse specifically so that if you take an x value and you go cos inverse of that, you will get one answer and one answer only, right? So this y value ought to correspond to that x value, right? So when you put cos inverse of minus root 3 on 2 into your calculator, because your calculator is thinking on this, right, you should get 5 pi on 6. So my diagram is horribly off scale because let's just end it there. That's better. Anyway, okay. So 5, that's not a square root sign, that's a 5. Okay, so 150 degrees, right? That's how high you've gone up. So that's what this measurement here is, 5 pi on 6, okay? So what's the area of my rectangle? It's length times height. Okay, good. Now, be careful here. In the previous questions, like this one, right, I subtracted an area, okay? Of course I subtracted an area because, you know, I was trying to take a difference, right? But I shouldn't subtract an area this time. Why not? That's right. Because it's already under the axis, right? I actually want to add whatever this integral is, because this integral will be negative when I work it out.
Subtract the absolute value of the area.
I suppose you could. I mean, it's having much the same effect. Okay. But I think you're better off drawing your diagram properly, saying that's going to be a negative result. So I'm going to add it rather than subtract. All right. What's the integral? What are my upper and lower bounds? I've already worked out the upper bound. What's the lower bound? Thank you. Okay, and in some senses, that's really all the hard work, right? We can go from there. Okay. Now, I do just want to draw out the fact that because all of these trig functions, right? They're all kind of the same function, just moved around or flipped upside down, all of that kind of thing, okay? So when you look at this, you might be thinking, gross, some kind of weird boundaries, right? Can anyone think of an easier set of boundaries, or an easier pair of boundaries, that would give us the same area? Anyone think? Look at that shape down there. This shape down here. What could you choose? Yes. Okay, let's think about that. So this shape down here, right? This part of cos, okay? What it corresponds to is this part of sine. Okay, it's just upside down. Okay. Now what's that distance there? From pi on 2 to 5 pi on 6. That's 90 to 150. Yeah, it's 60 degrees or pi on 3 radians, right? So this is the same as going from 0 to pi on 3, that area there, of sine. Okay? So you could just as equally, though notice it's positive rather than negative, okay? So if you don't like this, okay, you could just as fairly have said, let's subtract the area from 0 to pi on 3 of sine x, okay? The whole point, you might think, well, that's kind of weird. Why are we, the question's about cos inverse and not sine. Well, we're kind of artificially imposing on it these other functions anyway. This doesn't come from the original function, right? We just know that this area is equivalent to what we're trying to subtract. Just like this is, okay? So long as you draw your diagram well, you can actually pick whatever equivalent area you like, so long as it's actually going to give you the right value. And sometimes, you know, for instance with the 0 there, it'll give you some slightly nicer to evaluate function values, okay?